long as for at least we'll have the audio.
And we're going to go over inductance. Now, the first topic that your textbook talks about is something called mutual inductance. If I have a coil, okay, and I have a second coil, the idea is this. If I have two different coils, if I put a changing current in one of those coils, so I take a current that's changing here, I can induce a voltage in the other one. Okay, I can induce a current in the other one, and vice versa. I just need us to keep track of that. Okay, so what we have is we have this, so this will be 1, and so I can induce another current in here. So if I have I1, I'm renumbering these to put the 1 on the left and the 2 on the right. And I have some I2 over here. What this one does is this can induces a current in the second one. And so what we get is we get that the voltage that's induced in the second one, the voltage that's induced in the second one, okay, is equal to the number of coils in that second one multiplied by the change in flux that's in the second one. Okay? So it's the number of coils minus the number of coils in the second one times the change in magnetic flux in the second one divided by dt. I'm sorry. The derivative of that with respect to time. Now the thing is that what we say is when this first one, if the current here is changing, this I1 is changing, you're going to induce a voltage in I2. If this one, or I could do it the other way. I could say that I2 is changing and induce the voltage in I1. Now, because of the overlap between the fluxes here, I could do it either way. This is what we call mutual inductance. So when we talk about mutual inductance, we then say that E2 would be equal to the mutual inductance of this thing minus the mutual inductance between 2, 1, multiplied by the change in the current of the first one, dt. So we have the change in the current in the first dt instead of doing this. So in other words, we define this mutual inductance in such a way that when we're talking about the change in flux, we don't have to derive the change in flux anymore. We reduce that to the effect of the change in the current itself. Because it's a change in current in this first one that will cause that change in the magnetic field, that will cause that change in the magnetic flux, which will then induce in the second one. Now, of course, we call it mutual inductance. This is mutual. If I did the other way, this would be the same. So I can say that the voltage in E1, would be equal to minus mutual inductance 1, 2, dI2. And of course, we're calling it mutual inductance. So guess what we say when we say mutual inductance? The mutual inductance of the two coils is equal, the same. That's what we talk about mutual inductance. It's the same. So we define the mutual inductance between two coils. So if I have two separate coils, the mutual inductance there is, it can either be described as the number of coils in 2 multiplied by the flux produced in coil 2 by coil 1 divided by current 1. So in other words, if I put a current in 1, in the first one, how much flux do I get in the second one? Or I can equally say that this is equal to the number of coils in one multiplied by the flux that I get in one divided by the current that I produced in two. And both are the same. And both are the same. The units of this mutual inductance we look at the units, well, N doesn't have any units in it, it's just a number. We have the units of flux, which are Weber. And we have a unit of current, which is ampere. So we have a Weber per ampere, and we define this current of inductance as being a Henry. Somebody's uncle, I guess, I don't know. Okay, well, they talk about drawbacks of mutual inductance, and they give you a couple of problems with mutual inductance, and we don't use mutual inductance that much. So, just, you know. All right, now let's take a look at a single coil. What if we don't have two coils, instead we just have one? So we shift to the point where we just have one coil. Try to draw this bigger because I'm trying to stay toward the middle because, you know, it's. So I have one coil. And let's say that I put a current in it. So I can put a current I. Now, so we just have one current. One coil now and one current I. Okay, one coil, one current. What if we change that current? What if we now change the current? So now we're going to have that current be changing. Okay? So I have a loop, and I have a changing current in that loop. Well, that's going to change that magnetic field that's inside of that loop, that's created by that loop. Okay? So I have a loop, I change a current, which changes the magnetic field inside of that loop, which changes the flux inside of that loop. It's a loop. I'm trying to change the current inside of that loop. I'm trying to change the magnetic flux inside of that loop by turning up the battery or turning up whatever it is I'm doing outside. The loop will respond. The loop will respond by fighting the change in the current. So because I've done this, the loop's going to respond. So even if it's just one coil, if I go to change that current, that loop's going to respond in kind. It's going to respond producing a voltage back the other way to try to stop me from changing that current. If I try to increase the current in this, the loop is going to produce a voltage to try to decrease that. If I try to decrease the current in this, the loop's going to produce a voltage to try to increase the current. The loop will respond to itself. So it doesn't have to be completely. The external agent is whatever we're trying to do out here. But the loop, even if the magnetic field is produced by the loop itself, the loop will still respond. And this is what we call self-inductance. This is self-inductance. And the way we define it, we use the capital letter L. Just because we use capital letter I for current and everything else, so capital letter L for inductance. Okay? Inductance is the number of loops multiplied by the magnetic flux produced when a current is put in itself. When you put the current in itself, how much magnetic flux is produced. And then the voltage across the inductance is minus the number of, because we already included the number of loops, is simply minus the inductance that we've calculated multiplied by di dt, where that's the current in the inductor. We can actually calculate the inductance or find a formula for the inductance of a solenoid. So let's take our solenoid. Here's our solenoid. And we want to figure out a formula for the inductance of that solenoid, the self-inductance. Okay? So we say that that self-inductance is equal to the number of loops multiplied by the flux produced by that, divided by the current that I have to put in it. The current that I have to put in it. Now that inductance itself, even though it's defined in terms of current, if I were to solve it for a particular geometry here, which is this geometry of the solenoid, it shouldn't depend on the current, because this inductance is supposed to be a property of the coil itself. Okay? This is your last circuit element that we have this semester, and we're going to call this an inductor. So it's an inductor. And we're going to note the self-inductance of it. Don't need that piece of junk anymore. Okay? So this is the inductor. So let's do this for a solenoid. Let's take a look at this for a solenoid. All right, so we put a current I in here, and it has a number of loops in. Okay? And so this L, I want to put it a little different. I'm going to make the length, say that the length of this is little l, like that. Little l. And the reason why I want to say little l is because capital L is now the inductance. Okay? Capital L is now the inductance. All right, so we want to know the flux through this loop, through that loop, when I put a current I in it. Well, the flux, remember, is the magnetic field multiplied by the area multiplied by the cosine of the angle between those two. Since the magnetic field in this case would be going straight through the inductor, the factor of cosine of phi is 1, as in most of the cases that we have around here. So we just need the magnetic field inside the solenoid, and we have a little formula for that. It's mu naught little n times the current in that solenoid. That's our magnetic field side of the solenoid, and it's multiplied by the cross-sectional area of the solenoid. So we plug this back into our formula for this, and I want to break this little n up. The reason why I want to break this little n up is because I have another factor of capital N, which that little n involves. Because the little n is capital N divided by the length of the solenoid. It's the number of loops per unit length. So I have L equals N mu naught capital N I, the little l comes down here. I have an I down here and the area. And so finally we can get our geometry formula for the inductance of a solenoid. Looks like this. It's mu naught n squared area divided by the length of the solenoid itself. kind of makes sense because notice that for the same density of wires that I have wrapped up, if I make it longer, I'm going to get more inductance because I'm just simply going to have more longer wire. However, for the same number of coils, if I have the same number of coils, if I spread them out over a longer area, I'll make the inductance less if I have the same number of coils. So it depends on whether you're making it just as dense or whether you're using the same number of coils. So in other words, if I had a limited wire, to try to maximize my inductance, I would need to be careful about how to manipulate these variables here. Because I have a certain number, but also it would depend on the area that I wrap around. So in other words, if I wrapped around, I could get more number of loops by simply making the size of the coil smaller, but then I lose out on the area. Or I can make a larger area, but then I lose out on the number.
When you say that, do you mean like how tightly wound it is?
Yeah, in other words, if I have a specific length of wire here, the area is the area of the coil itself, which is the area of one of these loops. That would be the area. Okay, so this is our final current element. Isn't that exciting? So when we put these in a circuit, and we talk about the voltage drop across them, when we treat them in a circuit, the voltage drop is simply the induced voltage. Okay? Except for when we talk about, in terms of voltage drop, we don't say that it's a voltage drop, even though it is in the opposite direction. We just put it as an absolute type thing. So we say the voltage across an inductor is equal to L di dt. Voltage across the resistor, what was that? IR. Yeah. Oh. Forget that. All right. So R. And the voltage across the capacitor was what? This one? Q over C, capacitance. Okay? So there's our circuit elements now. Okay? So we're adding that inductor to it. So we say that this is L di dt. And we represent an inductor in a circuit with might as well just finish my chart over here. Okay, so the inductor looks like this. Kind of draw a little spring in your resistor. What was it? Remember what it looked like? Long sawtooth. And the capacitor, there's a couple of symbols for it, but the one we generally use is the two parallel lines. Sometimes they use a line with a curved line on the other side, depending on how fancy you want to get and how specific you want to get. But these are your basic circuit elements. We're going to look at. Okay, so what we want to do is we want to look at the energy that's stored in an inductor. So the energy stored in an inductor. Let me go back this way toward the middle here. Talk about the energy. For the capacitor, we could do the energy by integrating over the charges going onto that capacitor. Yeah, I know, nightmare sounds good. But we just really concentrate on the result of it. So the energy in the capacitor is 1/2 QV. 1/2 QV. Or if I wanted to put it in terms of something else, let me go ahead and change this to charge and capacitance. Charge and capacitance. So that would be Q squared over C. Q squared over C. And by the way to switch between any of those three formulas there is to simply use this relationship, substitute in here for the one you don't want, and you'll get the other two. So you can just cycle back and forth whichever one I want. Okay? There's a reason why I wanted this one, because the others I want to put in terms of the geometric, the capacitance, resistance, or the inductance, which is our new one, and what it's storing. In this case, it's storing the charge. So with the voltage across the resistor. Now, resistors do not store energy. Resistors do not store energy. Resistors dissipate energy. So in terms of the resistor, we don't have an energy, we have a power. We talk about the power dissipated by a resistor. And that power, called from 4 weeks ago, 4 weeks ago, let's put back there, okay, is the current squared multiplied by resistance. Now, an inductor is different because there's energy actually stored in an inductor. That's the power dissipated by a resistor. So that's when we talk about a resistor in terms of energy. We talk about power dissipated. We don't talk about storing anything. We're not storing it. But in an inductor, we do store energy. We store energy because if I shut off the source for this inductor, let's say that I have current going through this inductor, and I somehow shut off the source, well, that thing is not immediately going to stop because there's flux in there. And that flux is going to resist changes to the flux. And so there's still going to be a back push if I try to decrease this current. You can't just immediately shut this current off. So there is energy stored in there. Just like if I turned off something and I still have those charges in the capacitor there. So I still have those charges. So an inductor is a circuit device that will actually store current. There's current that will resist changes because it's an inductor, because we've turned it in a loop, because you make something into a loop and all of a sudden oh my goodness, it doesn't want to go off. Current just keeps on going. So I could derive it for you, but I'm not going to. So the energy stored in an inductor is 1/2 L. Okay, so now let's go back and do one more thing that we did before with these energies, way before. Okay? So I'm going back again. So part of this chapter, of course, is review of the other circuit stuff, because this is our circuit stuff again. We're back on circuits. So you notice how I flew through the mutual inductance and then I hurried and got to the circuit? All right, so here we go. Way back. When we took a look at capacitors, we said we could think of the energy stored as in the charge. The energy stored in the charge. But if we look at what's inside the capacitor itself, we can also think of the energy stored as being in the electric field that's inside the capacitor. And then we did a big calculation and we found out, well, we couldn't explicitly talk about the energy, but we could talk about an energy density associated with an electric field. And so we got an equation that looks like this. So the energy density for the electric field is, make sure I got the factors right. 1/2 epsilon naught times the electric field squared. Okay? All right, now I'm going to do the same thing with the magnetic field, using this and the solenoid to kind of derive it for the solenoid, except for we're going to say it's in general. Here's my derivation. you can read it, okay? So here it is. It's going to look pretty familiar. There's a factor of a half. That shouldn't surprise anybody because there was a factor of a half in the electric field one, right? Factor of a half in the electric field one. Oh, the factor of half in the magnetic field one. Look, this one has E squared in it. Guess what this one's going to have? B squared, see? The only difference is where that constant ends up going. And it's just the way we define the constant. The mu naught goes in the denominator. And so they each got their constant, except for the only difference is the magnetic one, the constant's in the denominator. Okay? So that's our energy density, and that's energy per unit volume. The energy density of a magnetic field. All right, now we get our first circuit. We get our first circuit with an inductor in it. Okay, so here we go. So we're still in DC. So we're still going to work with DC. So I got a battery. Connected to a switch. That switch is then connected to a resistor. And an inductor. Ta-da! So we have a resistor and an inductor connected. And I do want to be consistent with the textbook in what they're calling this. That is fine. They're calling it E. It's fine. Let's call this E. E. All right, so you close the switch at t equals 0. You close the switch at t equals 0, and then we're going to use Kirchhoff's law to solve for this thing, or the loop equation, if you will. There is only one current in it because there's only one path to follow, so we don't have to worry about any junctions here. So what we get here is we get E minus the voltage drop across that resistor, which is I times R, minus the voltage drop across that, which is L di dt. And that has to equal 0. Fun times had for everybody. They actually go over the derivation in the book using all the fun calculus and everything. Yay! Or boo. So what you get as a result of all this is the current as a function of time is equal to E over R multiplied by 1 minus E to the minus T over L over R. Now, let me change this a little bit. I'm going to replace this L over R with another tau, time constant, and I'm going to come over here and say here tau is equal to L over R. Does that look familiar? Yeah, it's just what happened to the charge in an LC circuit. It's just what happens to the charge in an LC circuit. This circuit will build up current. So the LR circuit builds up current. So you close the switch here, close the switch at t equals 0. And at first what happens is that inductor says, you ain't putting no current in me. I got no flux and I don't want no flux. So initially the current is 0. As time goes on, the current builds up in the inductor, and then it's fine. Okay? So after a long time, so if we look at the way that the voltage works, at first all of the voltage is across this inductor. Okay? You have a maximum change in the current. The current itself is 0, you have maximum change in current. And then slowly you get built up a steady current, and the inductor doesn't matter anymore. Okay. So inductors block current at first, and then once they build up current, they let it flow freely. Notice that's just the opposite of a capacitor. That'll become important a little bit later. Capacitor at first, when it's uncharged, lets current flow freely, blocks it after it's charged. Inductors don't. Inductors block the current at first, let it flow freely later after it builds up. Okay. The other equation we can look at here is dIdt. But we don't really have a dIdt variable that we look at. I mean, we can look at this. And then this looks like what would happen with the resistor. It's the E over, where we go, E over L, that's it. So it's E over L, E to the minus T over tau. Now, of course, switching this off is a bit of a problem because if I were to switch this off, you get some weird stuff going on here with the inductor because the current can't flow, but it has to flow for a little bit. So we really wouldn't want to open a switch like this. So let me give you a different situation where we can open the switch, okay? So let's say we have this situation over here. Where, let's see, do I want to switch it? Well, your book has it where it opens one switch and closes another or something like that. It's kind of weird. Let's say that we have this going like this. Let's say that I have a resistor here. And I have an inductor. And then give me another resistor over here. There we go. So I'll call this R1, R2. And this is my inductor L. And this is my voltage E. You want numbers?
Sure.
Okay. 10 volts of 5 ohms, 2 ohms, and 3 Henrys. That's a huge number, by the way. 3 Henrys is huge. Let you know. Most things are in like the millihenry range. It's not as far-fetched as the 3 farad capacitor, but 3 Henry inductors are very big. All right, so now let's say that the switch has been closed for a long time. Okay, so we closed the switch for a long time. Okay. Question for you. Okay, the switch has been closed for a long time. Let's first of all find out what the current is in the inductor. The switch has been closed for a long time. Okay, if the switch has been closed for a long time, this no longer blocks current at all. Current freely flows through this, which means that all of the current will go through your inductor. None of it will go through this. Which means that with this closed, this is equivalent to this. And the only resistance you have here is the 5 ohms. The only resistance you have is the 5 ohms, so therefore your current, a long time after that switch has been closed, is 2 amps. How did I get that? 10 volts divided by 5 ohms is 2 amps. Now, there will always be some resistance inside of an inductor. There has to be, because the inductor is made of wire. That wire will also have resistance. But we're neglecting that resistance compared to 2 ohms. Because whatever copper wire 10 to the negative 4 or 5 ohms is really, really small. Unless they made it out of plastic, but I don't think you'd want to make inductors out of plastic. It's kind of hard to put current in them. All right, so we got to it. Then we open the switch. Okay? We open a switch, and then we ask, what happens after we open that switch? Well, immediately after we open the switch, the current is going to continue to flow. Since I did give it a path, there won't be any weirdness here. I do kind of want to give you a current. Okay. So I gave it that. So it's going to flow through this 2 ohm resistor now. So you can think of it as the inductor discharging through the 2, or discurrenting, I guess. Like, if that's a word or not. So it drains its current through the 2 ohm resistor, is what it does. Because this current is flowing 2 amps down this way. So immediately after that switch is closed, it's going to go, oh, push the 2 amps. It's going to keep pushing it. So it's going to push it through here, yes. So it's going to push it through there. And so then the inductor will begin to drain the charge. So the charge will begin to come off of the inductor. Yes?
You're saying closed, but you have to be open to it, right?
Yes, open, sorry, open. It was closed for a long time, and then we opened it. So right after we open the switch, the current is going to push, the inductor is going to push the current through there. Just like a capacitor would. You know, if I had charge on a capacitor, when I open a switch, if I no longer have that battery pushing the current, then the charge itself will start to flow off. In this case, I have the inductor is going to start pushing current through here. Yes?
But why does it go to the resistor instead of the battery?
Because there's no way to get around here. See, that's what's wrong with this diagram. That's why I said it's weird. Because if I opened the switch again after it was closed for a long time, there'd be it's just weird, because what would happen is that the actual inductor would try to push current. It would try to push it into the battery because that's the only place for it to push it. But then it wouldn't want to go to the battery because it's kind of ended up here. Then you'd have to treat this kind of like a weird, very, very small capacitor. Would very quickly drain it, and your wires would kind of get hot, and you wouldn't want to do that. You don't want to just cut off it. Yeah?
So when you close that first?
When we closed it at first, okay. When we closed it at very first, the situation is going to be like that one over there. In other words, at first there will be no current through this. All the current will be over here. Okay? So at first it will do this, because current can't flow through here at first. Then slowly, after the current builds up in this, all the current flows through here. Then after I open it up, what happens is that current then pushes through this.
And when you say slowly builds up, do you mean that they are like in the middle, do they like both have current, or?
Well, what happens is that this one slowly builds up current as the current decreases in this one.
Okay.
So as this one builds up current flowing through it, current will decrease in this one. And what happens is that if you look at this, if you look at the current with your charging or your putting current into an inductor, it's always this exponential function that kind of builds up quickly at first and then slowly as the time goes on to the maximum E over R, where the inductors neglect. Yes?
Why is it released counterclockwise instead of clockwise?
Now, after you open up this switch, this is pushing current downward like this. Okay? It can't go that way. That way's blocked. It has to go this way. Okay? Because that current has to stay the same. The current was 2 amps flowing downward. The current has to stay 2 amps flowing downward, at least immediately after, and then it will slowly dissipate through that resistor. So what happens is that after you open the switch, the current ends up decreasing. So your current in the circuit is equal to the initial current that you had in the circuit, multiplied by e to the minus t over tau, where tau for our L our L circuit is L over R. Yes.
If you had the inductor, if you had it in series,
Okay, the inductor is in series with this one here, yes.
I don't know if you had it in series with
The whole thing. You back over here. And I open the switch, yeah, so you see what I mean? I can't, I'm trying to get a realistic situation where if you had the current in here, because your book shows you this. Your book shows you an R, it shows you something like this. It has an R and an L, and somehow you magically got current in here, and you close the switch. But the problem is, how can you have current before you close the switch? Your book's kind of silly that way. You know, you can't have current before you close it. Yes.
When you say tau equals L over R,
Mm-hmm.
the R is the
Resistance
of the wire, right?
of the resistor, yeah. Of this resistor
that
right here,
one?
yeah.
Oh.
Mhm. Yeah, we are neglecting the resistance of the wires that make the inductor itself, compared to whatever other resistor we put in there. Now, there are ways to experiment with an inductor that you can make some plots and actually figure out its internal resistance of an inductor. Not easy to do, and you have to use certain external resistors, and you make a plot of how the current is going, and then you kind of see, okay, what's the total resistance in this circuit here, and then I subtract off the resistance of a resistor and kind of get the internal resistance. Yes, go ahead.
At the beginning of the example, you said that with a closed switch for a long time,
Mhm.
we were doing 5 ohms and it wasn't flowing to 2 ohms. That's because the current doesn't want to go through additional resistance.
Right. All right, maybe I should be better. How about if I started with a new example? Let's do a whole new example. You want to do a whole new example?
Sure.
Let's do a whole new example. All right. We have plenty of time. All right, let's see. Let's have this. This time we're going to do this one. This time I'm going to do one resistor and okay. I'm going to make this thing be 15 volts. I'm going to make this thing be 5 ohm. And I'm going to make this thing be 2 volts. I'm going to go over here and I'm going to put this thing down and this. There. Here's a situation where we have everything we need. We have everything we need. Okay? Okay, so I begin by closing the switch. I begin the experiment by closing the switch. Okay? So I start by closing the switch. Now, immediately after I close the switch, I want to know what is the current through the 5 ohm resistor, and what is the current through the 10 ohm resistor. Okay? immediately after I close the switch. Okay, well the current through the 10 ohm resistor should be simple. Literally what I have here is when I have this parallel circuit hooked up like this, I literally have two different circuits going on. Here I have two different circuits going on. I have one that's got 10 ohm resistor that goes back to ground, and that's it. So how much current is flowing through that 10 ohm resistor? 1.5 amps. So here there's 1.5 amps. Okay, 1.5 amps. Now, how much is flowing through the 5 ohm resistor? Nothing, because the inductor will block it. Okay, so immediately after it closes, 1.5 amps there, none through the 5 ohm resistor, because the inductor will block it. Now we wait our first long time. Our first long time. Okay? So now that we've waited, we want to again take a look at the current through the 5 ohm resistor and the 10 ohm resistor. Okay, so what's the current through the 10 ohm resistor?
Nothing.
Well, see, because I've added this resistance to this wire here, because I've added this resistor, there will be some current flowing through the 10 ohm resistor now. Okay? So how much is flowing through that 10 ohm resistor now? 1.5 amps. Because that voltage still has to be 15 volts as long as that circuit's closed. So as long as the circuit is closed, that voltage has to be 15. So that's 1.5 amps. What about the 5 ohm resistor? How much current is flowing through the 5 ohm resistor? 3. Because after a long time, that current is built up in the inductor. It no longer provides any resistance to the current, and therefore the 5 ohm resistor is all the resistance that's there, so you get 3 ohms. 3.0 amps, sorry. Yes.
How come when you first close the switch,
Mhm.
the 5 ohm resistor wouldn't be 3 amps, have 3 amps current?
Because the inductor will block that current.
But when you close the switch, I mean,
Well, yeah, because anytime I start to put current into an inductor, that inductor will block it. Because before I close the switch, there's no current in the inductor. Okay? So when I block the switch, if I look immediately after that switch is closed, even though I've got a path, that inductor will say, you are not sticking current in me. You keep your current. I don't want it. Not in my inductor. So it takes a long time to overcome that and build up the current. Okay. Now, we're going to open the switch again. After a long time, we've now opened the switch. And we want to look at where that current is. Okay? So what would be the current in the circuit after I open the switch? Would it be the current through the 10 ohm resistor or the current in the 5 ohm resistor?
good question.
Which thing is preserving its current? The inductor is what preserves the current. The resistors, I don't care. I can shut off a resistor. There. get them to come back on again, apparently. But the inductor, you can't immediately shut off. Because once it has current, it's not going to let it go. Mine. Mine. Okay? It's like a 2-year-old kid. Mine. So once it has that current, it wants to keep it. See, it's not satisfied with any changes. Okay? So it's that's going to drive the current. So when you start out with current in this case, the current that we start out with is what was in the inductor, which is 3 amps. So what happens is as soon as I open this up, the 3 amps does this. It does that. That's where the current goes. The inductor pushes that current of 3 amps through the remaining circuit elements. Once the battery's not there driving it. See, when the switch was closed, we had that battery driving the current. But once that battery's done driving it, oh, my inductors are fine. Don't you take that current away from me. So we start out with 3 amps, and the inductor discurrents or discharges or whatever you want to think of it, through those other 2 resistors. So if we were to take a look at this, we could actually write down a formula for the current as a function of time. The current is a function of time because it's, remember that this is now a discharging inductor. It says I naught e to the minus t over tau. Tau is L over R. Which resistor are we talking about here?
The one you add in series.
Aha, somebody, yes, you add them in series. Because it's discharging through both in series. And it does have to go through both. So the resistance here is 15 ohms. The inductance is 2 henries. So this time constant is going to be, what is that? That's not very big. Somebody divide that and tell me what it is. .745?
No, 7.5.
Really?
No.
Wow, that's amazing.
It's 0.1333.
0.133, okay, 0.133. So notice that this isn't going to take very long, even with my giant inductance there. It doesn't take very long for this thing to really kind of dissipate, that current to dissipate, because my time constant here is only 0.1333. I wait 1 second, I've already passed up like 6 time constants here. So it's going to be very small, but that's 0.133.
That's tau.
That's tau. That's tau. It's the inductance divided by the resistance. And so then we get our current is equal to 3 amps e to the minus t over 0.133 seconds. And in fact, I'm going to suppress my units. So 3 has units of amps. The amps is amps. T of course has units of seconds, as does our time constant tau. So a henry divided by an ohm is a second.
Why isn't I not the 1.5?
Because the 10 ohm resistor isn't driving its current.
Well, isn't when we close the switch it was 1.5? Oh.
You see what I mean?
Yeah.
So in other words, when we have the switch closed, we've got 3 amps going through here, and we've got 1.5 amps going through here. Okay? When we open up the switch, this isn't driving its current, but this is. So this is actually going to just push the current the other way. So the current it's driving is going to do this when we open the switch. Okay? Because the resistor doesn't drive its current. By the way, with the switch closed, what is driving that resistor's current? The battery. The battery's driving. When we open it up, that battery's no longer driving the thing. The inductor is the only thing that's going to push its current. Oh, cool. Hopefully this thing will be fixed on Wednesday. That was not a happy welcome. Okay. Anyway, thank you.